Hi everyone, welcome to Cloud Computing series. Yes, we have discussed still some design objectives and we are starting from scalable computing trends and new paradigms. Yes, see, technology follows patterns that help improve computing over time. Yes, these patterns help developers to predict how computers will evolve in the future. For example, we expected computers to get faster and smaller. Yes, and that's exactly what happened. Yes, early mobile phones were big and slow, but today we have powerful smartphones that fit in our pockets. See, engineers and programmers study trends to prepare for future advancements. Yes, this helps. This helps them design a better software and hardware that won't become outdated too soon. For example, tech companies like Apple and Google plan years in advance to make sure their products stay relevant. Yes, Jim Gray was a computer scientist, yes, who studied how technology shapes software and vice versa. For example, when internet speeds improved, platforms like a YouTube and a Netflix became a possible, right? When cloud storage got cheaper, services like a Google Drive and a Dropbox became popular. Gordon Moore observed that computer chips double in power every 18 months. Yes, this means computers become faster, smaller, and cheaper over time. For example, video games today look much better than they did 10 years ago, thanks to faster processors. For the past 30 years, Moore's law has been accurate, but it may slow down. Yes, as the chips become smaller, making them even faster becomes more difficult and expensive. The companies like Intel and AMD are finding a new ways to keep improving speed. And next is, see, George Gilder predicted that network speeds would double every year. Yes, this helped streaming, cloud gaming, and online services grow rapidly. For example, early internet was slow and cloud barely load images. Yes, see, today we have a 5G, fiber optic internet, and cloud gaming. Yes, all thanks to faster network speeds. See, the demand for a cheaper and a faster devices like desktops, laptops, and tablets pushed the tech industry forward. Yes, this also helped big data centers and cloud computing grow. Example, laptops used to be expensive and only for businesses. Now almost everyone has one. Yes, cloud services like AWS and Google Cloud became popular because cheaper hardware made them possible. Distributed systems connect many computers together to work, yes, as a one powerful system. They focus on sharing resources and running many tasks simultaneously. For example, Google search uses thousands of computers working together to deliver search results instantly. Yes, then Bitcoin mining relies on many computers solving complex problems simultaneously. See here, degrees of parallelism means how many tasks a computer system can run simultaneously. Yes, it measures how much work can be done in a parallel instead of one after the another. So moving to the next, see, before discussing the special requirements for distributed computing, first we'll see degrees of parallelism. See, over the past 50 years, computers have evolved from slow and bulky machines to powerful and high speed processors by improving parallelism at a different levels. Yes, the first level is bit level parallelism. Yes, in the early days, computers could only process one bit at a time. Yes, gradually, computers increased their word size to process multiple bits simultaneously. Computers used 4-bit processors, then moved to 8-bit, then 16-bit. 32-bit and now 64-bit CPUs. Yes, this made a computers much faster by handling a more data at a time. Yes, and the next is instead of doing a one instruction at a time, processors started handling a multiple instructions at once. Yes, this made a computers way faster. For example, if a cook cuts vegetables first, then boils water, then fries a food, it takes a long time. Yes, but if they boil water while cutting vegetables, things move faster. Yes, that's instruction level parallelism. Moving to the next. Different techniques have been used to make instruction level parallelism more efficient. Yes, see, using pipelining, superscalar computing, then VLIW, that is very long instruction word architectures, and multi-threading. Yes, pipelining works like an assembly line. New instructions start before the previous ones finish. Yes, in the superscalar computing, the processor executes multiple instructions at the same time. Then VLIW. The processors groups many instructions together and then executes them. Yes. Then in multi-threading, a program is split into smaller independent tasks. Yes, which run in a parallel. Yes, the next is ILP, that is instruction level parallelism. Yes, it needs smart techniques to guess and manage tasks efficiently. Yes. In the branch prediction, the processor guesses which instruction will be needed for the next execution. Yes. Then in dynamic scheduling, the processor rearranges tasks to avoid waiting. In the speculation, the processor performs tasks in advance to save the time. Then in compiler support, special compiling software helps to optimize instruction level parallelism performance. And the next is data level parallelism. Yes, data level parallelism allows a processor to apply one instruction to many data points at the same time. This is useful in a graphics processing, scientific computing, and artificial intelligence. So for example, a photo editing software applies the same filter to thousands of pixels at once. Yes, instead of one at a time. That's data level parallelism. See, data level parallelism needs a special hardware like a GPUs and optimized softwares to function efficiently. See, multi-core processors have a many cores. So, we now try to run a different tasks on a different cores at the same time. So, today's computers use a bit level, instruction level, data level, and task level parallelism together to be as fast as possible. Bit level, instruction level, data level parallelism work well today because of improved hardware and software. Then the next point is, see, task level parallelism is a harder to implement because programming multiple core is complex. Yes, for example, a single threaded program works on one core easily. Yes, but making a program that divides a work across multiple cores is tricky. Yes, moving to the next point. In parallel processing, it is about making a one computer faster by using a multiple cores. Then distributed computing is about using a many computers together. But job level parallelism means splitting entire jobs across multiple machines. Yes, the next point is it is fair to say that coarse grain parallelism is built on top of fine grain parallelism. Yes, then what is fine grain parallelism? See, but it is nothing but a small scale parallelism. It improves single processors first, like instruction level and data level parallelism. Yes, then coarse grain means large scale parallelism. Yes, it comes next where multiple computers work together. Thanks for watching. If you are getting confusion in between, then pause the video and please make a note.